So good morning, good afternoon, and good evening, everyone. My name is Xiaocheng Mi. I'm currently a postdoc researcher at McGill University in Canada. So first of all, on behalf of the organizers of the Martinez Society, I would like to wish you a very happy, healthy, and productive 2021. And also welcome you all to the first TMS talk in the new year. Before introducing our speaker today, Professor Andrew Higgins, I would like to give you a brief introduction of the Martinez Society. So this is a non-profit organization that aims to build community for young scholars to freely and equally build connections, share their work, and exchange thoughts. Interdisciplinary exchange is our major focus. So as you can see here, the Martinez Society organizes three major series of events. The first one is the TMS talk. For these talks, we invite successful researchers in academia to share us about their cutting-edge research and innovations, as well as to popularize science in larger media. The second series is the WBA, or World Beyond Academia talk. For these talks, we invite promising young professionals from industry and also consulting business to share us stories about their career path and also open up our perspectives for the future path that young scholars can pursue. And the last one is the TMS workshop. The objective of this event is to help young scholars, especially graduate students, to develop diverse skill sets for their research activities and the future career. If you would like to know more about the Martinez Society and the upcoming events, please follow us on Twitter and WeChat by scanning the QR codes as shown below. And more information can be found on our official website, which is also linked here on this page. And also, if you have any questions, suggestions, or interests in sharing your research and the personal story in our future events, please feel free to contact us by email at the address given here. Next, I will let my co-host today, the founder of the Martinez Society, Dr. Jen In, to introduce our honored speaker today, Professor Andrew Higgins. So please go ahead, Dr. In.
Yeah, hello everyone, I'm Jen. I'm currently a postdoc fellow at Max Planck Institute for Intelligent Systems. My research focuses on bio-inspired structures, solid mechanics, and microrobotics. So personally, I'm a huge fan of sci-fi, and I have always been very fascinated by interstellar travel, and I believe it might be the ultimate solution for the sustainable survival of human civilizations. So I can see different kind of interstellar technologies in many sci-fis, like including the movie, the Interstellar, and a recent TV show called The Expanse. So is it just sci-fi, or is it coming to the real world now? Today we are honored to have Professor Andrew Higgins to share the current progress on engineering interstellar travel technology and also perspective to the future, for the future. So a little bit introduction on Professor Higgins. Professor Higgins is a professor of mechanical engineering at McGill University in Canada. He has 30 years of experience in high-speed compressible flow experimentation and modeling, and also on shock wave and detonation waves in gas phase and condensed phase materials, with applications to advanced aerospace propulsion and fusion energy. He served as managing editor of Shockwave and an editor of the Proceedings of the Combustion Institute. Professor Higgins founded the McGill Interstellar Flight Experimental Research Group dedicated to serious engineering of interstellar flights. So before starting the talk, Xiaocheng will briefly introduce the talk and the QA rules.
Yeah, so basically during the talk, please mute yourself. And if you have questions, you can use this raise hand function in the in chat and the Q&A, and we will promote you to the panelist at the end of the talk, so you can directly ask Professor Higgins your question, or if you prefer to type your question in chat, and we can read that to Professor Higgins at the end. And for the concerning of the time limit, we will ask each of the attendee ask no more than 2 questions. So yeah, and then I would like to give the podium to Professor Higgins. Please go ahead. Thank you.
Okay, thank you, Zhen and Xiaochen, for the very nice introduction, and I'm really honored and excited to be here. I think this is a wonderful initiative. You have probably if there's one silver lining to the very dark cloud of the pandemic that we've been living in for the last year, it's the fact that we found these new ways to collaborate with each other and create these new online forums. So it's just wonderful, and I just really admire your initiative and energy in creating this forum. So let me make sure my slides come up here. So yes, I'm Andrew Higgins. I'm a professor of mechanical engineering at McGill University in Montreal. And as Jen mentioned, my background is in aerospace. I did all my undergraduate, master's, PhD degrees in aerospace, although as I'll tell you today, it turns out most of that education really is almost useless when it comes to thinking about the problem of interstellar flight. The distances are so vast, the speeds required are so great that a lot of traditional aerospace engineering is really not applicable to the problem of interstellar flight. So I'll just say a few words about some of the other projects that I've done that sort of built up, that were steps I had to undertake to build up my confidence to take on something as daunting as considering interstellar flight. In a period over the last 15 years at McGill, we did a project where we developed a very high velocity gun, basically a kind of launcher to launch projectiles or pellets to very high speeds, up to 12 kilometers a second now, which is actually a world record. And this was mainly done for the problem of looking at orbital debris, spacecraft being hit by junk that's left in low Earth orbit, to be able to simulate those impacts in the laboratory. I also worked on propulsion applications of detonation. My background is in high-speed combustion, detonation, explosion. And so I, with my PhD student, Jimmy Verreau, looked at the existence and stability of oblique detonation waves. I've had a long interest in how we would include discrete effects, sort of mesoscale features in detonations. And this was actually the work of Xiaochen Mi, one of our hosts today. His PhD really greatly advanced our research agenda on this topic. I also now collaborate with a company in Canada that's attempting to commercialize fusion energy. Their concept involves some aspects of high-speed flow and shock waves. And so, although I'm not a plasma or fusion expert, I've been collaborating with them for the last 7 or 8 years. And finally, I was the principal investigator on a spaceflight experiment that flew on a European Space Agency sounding rocket in 2017 to look at using the microgravity environment to study flames in, again, particulate or discrete media. So all of these things have really been stepping stones to build up my academic credentials and also to build up my personal confidence to take on increasingly challenging projects, to really get back to something that predates even my undergraduate degree. What the real story of my life is that when I was a teenager in high school, I read a science fiction novel called Flight of the Dragonfly by Robert L. Forward. And this novel was about building an enormous sail in space that would be illuminated with an enormous laser, and the photon pressure of that laser could push this sail and a human crew that would be on board, to another star, Barnard's star in this case, which at the time there was thought maybe there might be an exoplanet around Barnard's star. That was later disproven, but the idea was very intriguing. And I remember flipping to the back of that book and reading the About the Author page, and it said that Robert L. Forward is an aerospace engineer at Hughes Aircraft. And I said at that point, this is what I want to do with my life. I want to dream and then do the engineering of these grand ideas, very, very challenging problems. And what was wonderful about Robert L. Forward is he would write not just a science fiction novel, but then he would often accompany that with a scientific publication. This is a paper that was published around the same time in the AIAA Journal of Spacecraft and Rockets, where he went through the engineering of how you would do this. So again, the idea is you build an enormous laser. As I recall in the novel, they built the laser at Mercury, hundreds of gigawatts of laser power, and then focus that onto a sail that would be thousands of kilometers in diameter. And to keep the laser focused on the sail, you would need to build an enormous lens, again, 1,000 kilometers diameter in space, because even the best lasers tend to spread out due to just the wave nature of light, due to diffraction. The beam would spread out, so you need to keep it collimated on the sail. Okay, and he even came up with an ingenious way to decelerate the sail when you got halfway to your target, and even later figure out a way to get the sail to come back to Earth to do a round trip. Okay, so Forward was a wonderful human being. Anyone that has met him will tell you what a warm personality. You can see kind of was flamboyant dresser and so on. And there's other people I think on the Zoom today that actually had the honor of meeting him, and can also tell you about what a wonderful person he was. And this is really the quote that gave a lot of people who are interstellar enthusiasts, gave us goosebumps when in the 1980s he declared that interstellar flight, while it's very, very difficult, it may take a century or more to prepare for this, it can't be considered impossible. It's probably the most difficult thing we could imagine doing, but it's not impossible. So why is it so difficult? So I'll just maybe give you a little introduction to just how difficult this is and why it's very different than traditional aerospace engineering missions we might do within the solar system. So if you ever go to the University of Colorado in Boulder, I think some of you have colleagues at this university, so you probably have a chance to visit this. Please go on campus and find this. It's a wonderful scaled model of the solar system. So there's a little, about the size of a grapefruit, a little gold sphere. And if you walk past that, you'll see a few feet away a little pedestal, and there'll be a little tiny speck of sand on that pedestal. Well, that little speck represents the planet Mercury in comparison to this sphere that is the sun. You walk to the next pedestal, Venus, next pedestal, that's Earth. Earth is a little teeny tiny, like the size of maybe a little peppercorn. There's Mars, and as you start to walk across campus, you'll find Jupiter, Saturn, and after about a 5-minute walk, you'll eventually get to Pluto. And this is the furthest planet, well, now dwarf planet that we have explored. And on the scale of that model, let me just ask, what do you think, how far would you have to actually go to get to the next star, to get to Alpha Centauri? Does anybody have a guess? Let me open up the chat here and see if I can. Maybe if anybody can just guess on this scale, how far away would you need to go to get to an exoplanet? Oops, I don't want to give the answer there. Oh, somebody says they can't see me share my screen. Is that right?
I can
miles
see your
away?
screen.
Miles? No. Guess further than that. 300 meters? Nope, you have to go further than that. 1,000 kilometers? Okay, M Safe is getting closer there. The answer is 4,000 kilometers. Okay, so on the scale of this model, if you read the fine print there, it says that the location of Alpha Centauri is about where the Panama Canal is in Central America in relation to Denver, Colorado. Okay, so it's enormous. Okay, I once did a scaled model like this in Montreal, and the distance of Alpha Centauri is from Montreal about where the Rocky Mountains are in British Columbia. Okay, you have to almost go all the way across Canada to get to the scaled equivalent. Okay, so it took the New Horizons spacecraft about a decade to get from launching from the Earth to Pluto. So if it took us a decade just to go the length of a soccer field. How long is it going to take us to get to the stars with our current technology? It will be tens of thousands of years. Okay, so we have launched spacecraft interstellar space, but it with the current technology would take tens of thousands of years for them to get to the stars. Okay, but if we could do that, if we could go the distances of light years, tens of light years, there's hundreds of stars out there, and we now know almost all of those stars have exoplanets orbiting them. So this is right now the count of exoplanets that we've discovered. You can see when I was an undergraduate student in the 1990s, it could be argued that maybe there are no planets. Maybe the solar system is unique. Maybe it's 1 in a billion that you have a stable, gravitationally stable system. But now we know, no, most planets are going to have, most stars are going to have planets about them. And you see this discovery rate has tapered off a little bit in recent years, but just wait, because there's a new spacecraft now. You see most of those earlier detections were from the Kepler spacecraft, but 2 years ago we launched the TESS spacecraft, which is going to be like Kepler, but for all the nearby stars. And it's very likely going to be discovering, just wait, in the next year or so, you'll start to see the data dumps coming from TESS, and there'll be thousands and thousands of new exoplanets discovered. Okay, so yes, we've sent 5 spacecraft to the stars: Pioneer 10, 11, Voyager 1 and 2, New Horizons. But because we used conventional rocket engines, where the delta V's, the velocity changes, are on the order of 10 kilometers a second, it's going to take tens of thousands of years to get there. If you want to learn about these, there's a wonderful documentary I highly recommend. I think it's still on Netflix, or if you're in the US, I think you can watch this on PBS for free. Online. It's called The Farthest, and it's a documentary about the Voyager 1 and Voyager 2 spacecraft, or you can read a very nice book by Jim Bell about the Voyager spacecraft. And I remember these as a child and as a teenager, watching these flybys, kind of the first flybys of the planets in our solar system, and just how thrilling these were. But this is essentially completed now. We've now completed the reconnaissance of all the planets in our solar system. And if you want to feel the thrill that these scientists felt as they got the excitement of seeing an image of a new planet for the first time, like Alan Stern did with the New Horizons flyby of Pluto in 2015, we're going to have to cast our gaze further out. We're going to have to think about going to exoplanets. Again, how did these missions were done? Well, they took a relatively small spacecraft, mounted it on top of some of the biggest rockets we had, and just threw them out of the solar system. But for an aerospace propulsion engineer, there was not a lot that was terribly innovative about these missions. In fact, all of the missions that we did to the outer solar system used a rocket engine called the RL-10. It's a liquid hydrogen, liquid oxygen engine that traces its lineage back to the 1950s. It's actually nothing new. All those missions were done with hardware that was really a relic of the Cold War and the 1960s space race. And there really was no new propulsion technology on those missions, and there's really not much of a prospect of using conventional chemical propulsion to get much further. And even electric propulsion, even in fact fusion propulsion, if we had it, would be a wonderful technology for zipping around the solar system. I mean, our host Jen mentioned the television show The Expanse. So all that technology is based on using fusion rockets, which is a wonderful way to get around the solar system, but really not fast enough to get us to the stars. So this is kind of where I was at in my career a few years ago, thinking about it would be nice to try to contribute to this. A very hard problem. There's a glimmer of an idea how we might be able to do this using lasers or directed energy or beamed energy. And this is sort of, I think, where I was at maybe 10 years ago in my career. After the previous 20 years before that, I had sort of ascended, as you do, by just publishing and working with outstanding graduate students and going to conferences. You sort of work your way up, and you're sitting on top of a hill, and you have people working under you that are coming, to sit and receive knowledge from you. But frankly, I was never very satisfied sitting on top of a hill like this. It's much more fun to be actually down here climbing the hill. And so I've always been in my career drawn to problems that I know no matter how hard I work, there's still much, much further to go. You know, it's for me, something I'm drawn to problems that no matter how hard we work at them, there's still always going to be much, much more to do, something you can really organize your whole life around. But kind of time was running out for me. So if you don't know PhD comics, I certainly, recommend watching these comics. And, you start out in your career saying, I'm going to research whatever I want. But as you go through the different stages of your career, when you actually get to the point where you can really research wherever you want, you're getting very, very near the end of your career. So I decided I'm kind of, I think, right about here in my career. So I decided it was time. Okay. And what really prompted me was a series of developments that were pointed out by Philip Lubin at University of California, Santa Barbara, who pointed out that there's been, I think the way I'm going to tell this story is there's been 4 developments that have really changed the game. Okay. And that grand vision that Robert O. Forward had from the 1980s of building the giant laser and the giant 1,000-kilometer sail might actually happen sooner than he had anticipated. So one of these developments is something called a fiber optic laser. And I actually have one of these in my lab. I've used it, Xiaochen and my other students have worked with this. I didn't really appreciate what this piece of equipment was, but it's a laser that the components inside the laser itself, if you open it up, the actual lasing medium, the laser cavity, is itself a piece of fiber optic glass. Okay, and because fiber optics have gotten enormously inexpensive because of the telecom revolution, these lasers have gotten very, very inexpensive. They've essentially followed something like Moore's law, that the cost per watt of these lasers, well, 20 years ago, it would have cost tens of thousands of dollars. If you ask the manufacturer of these lasers, they wouldn't normally advertise this information, but if you get to know them and ask them politely, they'll tell you the cost of these laser amplifiers is only about $1 a watt. Okay, so it's basically every 18 months it's gotten cheaper and cheaper and cheaper, and they've also gotten more and more powerful, again, following something like Moore's law. This is very unique. We don't normally in aerospace see things scale like they do in silicon. Okay, so we don't normally see propulsion technologies in aerospace evolve exponentially like this, but this is a technology that could. Okay, so the concept here, and again, this is from Philip Lubin's group in Santa Barbara, is you can combine each of these individual lasers together and make a giant phased array, because if you can keep all of the lasers phase locked, you can slightly shift the phase of the sine waves, the light waves coming out, and have them act like a giant optical element, like a giant lens, even though there is no lens. So each of these little individual lasers maybe would only be 100 watts, but you could combine millions of them together and make gigawatts of laser power. Okay, so this is what Philip Lubin's group is doing at UC Santa Barbara, and they're actually building these things. So this was enormously exciting to me as an experimentalist to see someone actually starting to work on the hardware of interstellar flight. The second development I'll tell you about is the fact that we now have very low absorptivity materials. So you might say, well, why can't we just turn up that laser even more powerful and push the sail even faster and get up to the speeds we need to get to the stars, which is about 20 or 30% the speed of light? Why can't we do that with a more intense laser? Well, the problem that Robert L. Forward faced in his design was that if you turn up the laser too much, you'll just melt the sail. Okay, so there's a limit to how much radiation flux you can put onto this. And Jeff Landis at NASA Glenn Research Center had studied this problem pretty intensely. And he came to the conclusion that you would be better off using a kind of a sail that's made from glass, that's made from a dielectric material. Now you might say, well, glass is transparent, but if you combine layers of glass together that have different indices of refraction, you can make a mirror. This is called a Bragg mirror. It's actually the same technology that's used on your eyeglasses. So if you're like me, if you ever look at your eyeglasses, there's this weird kind of purplish film on them. So that's an anti-reflective coating. And if you stack those coatings up in the correct order, you can actually make mirrors that are 99.99999 9, actually you can get to 6 nines now of reflectivity. So these kind of mirrors are used on the LIGO gravitational wave observatory, and they can basically bounce photons back and forth between mirrors like that hundreds of times, okay? The really important thing is not high reflectivity, it's more that you want low absorptivity. Because if you're going to put gigawatts of laser power onto the sail, if you absorb just a fraction of that percent, then you're just going to melt the sail. Okay. So again, because of fiber optics and telecommunication, we now have materials that only absorb a billionth of the light passing through them. And that's really the key. Okay. The third development I don't need to tell you about because a lot of you I know are computational researchers. So it's essentially the real Moore's law, okay, the revolution that's happened in computation over the last, well, really 70 years since Moore, first made his plot. I think he went back to the 1930s or 40s. I like to show this picture. When I got to University of Illinois in Urbana-Champaign in 1987, the first thing I did on campus was I went to the astronomy building, went up to the 7th floor, and peered through the window and saw a Cray XMP supercomputer. So at that time, University of Illinois was very fortunate. We actually had 3 of these Cray supercomputers on campus, most powerful computers in the world. And I was just obsessed to be able to use these. In fact, I did everything I could as an undergraduate to get into a lab that did computational fluid dynamics using a Cray. So by the time I was 19 or 20 years old, I was running code on a Cray. And those machines were capable of about 500 MFLOPS, 500 million floating point operations per second. Okay, well, 500 MFLOPS today is an iPhone 5. Okay, it's an iPhone. You can't even sell it. You know, you put that on Craigslist, nobody will take it. You know, you have to pay for someone to dispose of your old phone. I think Apple will take it back for free, but anybody else, you need to pay them to get rid of this 500 MFLOP computer that we all have in our pockets, right? So all of you know this, and the way we build supercomputers now is we take NVIDIA graphics cards and stack them up. So this is the supercomputer Beluga at McGill, which was, a year or two ago, the most powerful supercomputer in Canada. It's probably lost that spot now. But this is how we build computers now, okay? We leverage the enormous revolution that's happened in computation, and this is what we'll do to build our spacecraft. So this is what Philip Lubin's group is working on at UC Santa Barbara. This could actually be a spacecraft. That device right there, you see, has GPS, laser gyros, cameras, megapixel cameras, communications, lasers for communications, everything you'd need on a spacecraft, essentially built on a chip, on a wafer set, okay? So this picture was when I was there with my son in 2018. A year later in 2019, I visited UC Santa Barbara with some of my students. And this is just in a year now, you can see how much smaller it's gotten. So this is Nick Rupert, one of Philip Lubin's research scientists, with some of our students, Monica Sminskoff and Henson Liu there, okay? And people have flown these in space. So this is Zach Manchester. He's now at Carnegie Mellon. He's moved from Stanford to Carnegie Mellon, but he did this work when he was at Cornell with Mason Peck. And he has actually built and now flown in space little spacecraft the size of a postage stamp that can actually communicate back with the Earth, okay? The fourth revolution is something called adaptive optics. And this is a technique that's been developed by astronomers to essentially remove the turbulence out of the Earth's atmosphere that traditionally interferes with their astronomical observations. So if you look at a star at night and it twinkles, the star is not twinkling. What's twinkling is we're living at the bottom of a turbulent ocean. The Earth's atmosphere is turbulent, and that's what distorts the light. So if you look through, this is a view of the planet Neptune through the Very Large Telescope in Chile from the European Southern Observatory. But what astronomers can do now, with one click of the mouse, they can turn on software and control of a deformable mirror that's part of the telescope, and they can remove those distortions. They either use a nearby star that's like a fiducial, or they use a laser to create an artificial atmosphere, an artificial star in our own atmosphere. So with one click of the mouse, they can turn that image into this, okay? They can essentially remove the Earth's atmosphere. And the images they get now from the very large telescope in Chile are actually better than what we can get from the Hubble Space Telescope in orbit, because it's simply a larger mirror. Okay, so what we can do now is use this this technology, adaptive optics, in reverse. So we can now build the giant laser on the Earth and beam the laser to our sail in space. We don't need to build the laser in space. So again, Robert L. Forward's vision is that we would have to basically industrialize the solar system to build this very, very large laser in space. Maybe we can build it on Earth. So sort of what this would look like is, I think you know what this is. It's a solar thermal energy farm. It's kind of a solar farm where we're focusing mirrors onto a tower to generate solar energy. So this is not going to get us to the stars, but I just like to show this picture as sort of something familiar you've probably seen before to give you a feel for what the scale of this would need to be. So these are usually on kind of kilometer scale. We would need to build something like that that would be maybe on 10-kilometer scale. And the energy that we put out from that is about equal to the energy we get from the sun. So we get right now, it's a sunny day here in Montreal, I'm getting about a kilowatt per square meter of sunlight coming in through my window. If I can convert that with 50% efficiency to laser light, then we can put out about 500 watts per square meter of laser light. And if you do that over a 10-kilometer array, you can actually generate a gigawatt of laser, 100 gigawatts of laser power coming out, okay? So the laser that would come out from this array is, the flux is actually not that great. It's about comparable to sunlight, okay? So sometimes when people hear about this 100 gigawatt laser, they get terrified that it's gonna, you know, blow a hole in the Earth's atmosphere, or it's gonna vaporize, anything that's nearby it. You could actually walk, I wouldn't recommend it, but you could probably walk through that laser. It would be probably at 1 micron. Those fiber optic lasers operate at about 1 micron, so it's in the infrared. I mean, I wouldn't look into it, but it's not going to give you skin cancer or anything like that. But because of its large array and the fact that it's all the individual lasers are phased lock, this laser can now focus down onto a sail that's only 1 meter in diameter. Now the flux is enormous. Now we're at hundreds of gigawatts per square meter. Again, this sail, very, very thin, probably thinner than a micron, okay, but made out of reflective, but more importantly, low absorptivity material. So it would be made out of the same kind of materials we make fiber optics out of. So we don't absorb any of that light. And that, if you do the math on that, if you bounce those photons off, you'll be generating about 10,000 to 50,000 Gs of acceleration. Okay, so this will be accelerating at 10,000 Gs. You can't put a human on board, and since the sail only weighs about a gram, again, you need to use one of these kind of chipsets. Would be the spacecraft. But if you can do that for 3 minutes, at the end of that time, that sail will be going at 30% the speed of light. Okay, so it's incredible. This is probably the hardest part people have to wrap their head around. But the math is relatively straightforward. So just look up the momentum of photons. And if you bounce 100 gigawatts of photon flux off of a 1 gram sail, and you accelerate at maybe 30,000 Gs of acceleration, after 3 minutes, you'll be going 30% the speed of light. And then what you do is just coast the rest of the way to the stars. And then when you get there, right now we don't know of a good way to decelerate. We probably just do a flyby, very much like how Voyager did a flyby and New Horizons did a flyby of Pluto. And this sail will have a megapixel camera on board, and it will send the data back in the form of laser communication. Okay, so it'll have a little 1 watt laser, and it will direct that laser back towards the Earth. And this giant array that we have can also act as a telescope. So any well-engineered device can operate reversibly. Okay, so a photo emitter can also be a photo detector and so on. So this entire device can act like a receiver and pick up that weak 1 watt signal that's come back to Earth, and you can actually stream almost HD quality video back to the Earth as that sail flies through. Okay, so this all was put together by Philip Lubin in a paper. I'll put this let me put this in the chat. So if you have any questions right now, I'm going to put this in the chat, because everything I talked about is in here. And when this paper came out in 2015, it was like just a lightning bolt through my mind. I was a little bit upset that I didn't figure this out. Okay, there's really nothing in that paper you can't do with an undergraduate engineering or physics degree. And I just got very, very excited. I thought finally this vision that Robert L. Forward had is something that might actually happen in our lives. So I started going to conferences. There are workshops and so on in interstellar flight. There's Philip Lubin right there. And I met him in March of 2016 and mentioned I had a sabbatical coming up, and he was very welcoming. He said, please do come to Santa Barbara and work with us on this. With a lot of problems to solve. And he had mentioned that there was some interest possibly from a private investor that would put up some of the money to do the research on this. And about a month later, April 2016, it was announced that Stephen Hawking wants to send a tiny probe to the stars. Well, it wasn't Stephen Hawking. It was actually this individual here, Yuri Milner, who is a Silicon Valley billionaire. He started out in Russia. He created some of the early social media platforms that were used in Russia. And he's created a series of breakthrough initiatives to looking for life in the universe, looking for intelligence in the universe, and seeing if we can go and explore exoplanets. And so they had a big announcement in Washington, D.C. Here's Philip Lubin. This is Mae Jemison. She's a remarkable person. She's the first African-American woman in space, astronaut from the shuttle program in the 1990s. She has a foundation looking at interstellar flight. So all of a sudden, this became a mainstream topic. And the idea of sending sail to the stars using a giant laser with a tiny little spacecraft on board, or probably more likely integrated into the sail, became a real research topic. So when the Breakthrough Starshot Initiative was announced, they have a nice website. You can go look this up. Just Google Breakthrough Starshot, and lots of problems to solve. In fact, some of you, if you're hearing this for the first time, you're probably thinking, wait a minute, I can think of reasons why this isn't going to work. Okay, and there's a lot of good reasons that might be showstoppers. So they were very open and put up a list of about, what do I see here? Maybe 20 or 30 problems that might need to be solved. And I studied this list, and I thought there's some things here that as a mechanical or aerospace engineer, I might be able to contribute to. So one of the concerns is when you hit that giant laser onto this very, very thin, thinner than the kind of saran wrap you would use in the kitchen to wrap up your food with, how do you know that sail isn't just going to get crumpled up? Another big concern is dust. There's dust in our solar system. There's dust between the stars, and you're absolutely going to be impacting those dust grains. And at speeds 20, 30% the speed of light, those will be little tiny fusion bombs that are going to go off when you impact them. And I mentioned at the beginning, I had worked a little bit on the orbital debris problem, so I know a little bit about hypervelocity impact. I thought these could be problems I could contribute to. So again, the timing was very well. In 2018, I was available for sabbatical, and this is one of the really wonderful institutions we have in academia. At McGill, every 7 years, I'm allowed to take off a year from teaching and go and collaborate with colleagues around the world. It's not a completely free year. I mean, there's a little confusion about what sabbaticals are. It's you do typically have to write a proposal. You have to get letters of invitation, and you have to write a report when you get back to document what you actually did that year. But I had spent a previous sabbatical in 2011 at University of California, San Diego. And I find the University of California system is just wonderfully inclusive, egalitarian organization, very, very welcoming, very warm. And so I decided to go and spend my next sabbatical at UC Santa Barbara, which is a pretty wonderful place. Instead of spending a winter here in Montreal, to spend a winter in Santa Barbara, they have these wonderful little cottages for visiting scholars that's on a peninsula that sticks right out into the Pacific Ocean. And that turns out that is the main surf break that's in Santa Barbara. And I had spent my previous sabbatical in San Diego watching surfers for a year, but I never learned to surf, and spent the next 7 years, just kicking myself as I suffered Canadian winters that I didn't use that opportunity to learn to surf. So this time around, I didn't make that mistake. I went out, bought a surfboard, and would basically get up every morning, go surf for an hour, and then go into campus and basically try to engage with Philip Lubin's group, see what they were working on, but more importantly, see what they were not working on. You know, I didn't want to compete with them. Lubin, very interesting guy. His background is actually astronomy, cosmology, actually. He worked on the COBE satellite that first discovered the fluctuations in the cosmic microwave background, and came out of a kind of experimental cosmology, developing very sensitive instruments to detect cosmic microwave background. And that, you know, experience lent itself very well to kind of the development of these phased array lasers that are needed for his concept. And there wasn't much I can contribute to that. Okay, so it was very clear to me within days of arriving there that I was not going to come in and solve any problems. But I spent a lot of time talking to his very patient graduate students and postdocs about what they were working on to see where I could contribute in some other way. So when I came back to McGill in 2018, 2019, I basically decided to launch a group. And it was not a difficult sell to attract students to do this, because interest in spaceflight on campus is just exploding, okay? Essentially because of the spaceflight revolution that's happening now. So I and other engineering professors, you know, we call this the Elon effect, okay? So students are just enormously energized by what's happening in space. So am I. And so I found a way to sort of tap into this. You know, it's very easy to tell students that come to me with interest in doing, you know, something like SpaceX or Virgin Galactic or Blue Origin. I just, you know, say, well, you know, by the time you graduate, you know, Elon is already going to have a city on Mars. So if you want to do something really innovative, you need to, you know, cast your gaze out a little bit further and think about going to the stars. So it's been not difficult to recruit students to do work on this. Mostly now, though, with undergraduates. And this is kind of what I want to talk about now for the close of my talk is how do you create a research environment in a field that's traditionally considered science fiction or even fantasy? You know, how do we do this? And it would be difficult to right from the start hiring PhD students, because to be a PhD student, you need a community. You need to have a committee. You need to have people that can evaluate your dissertation and so on. So this sort of became the challenge. How do we create a community? So again, I have a fantastic group of undergraduates, very, very enthusiastic, that just, you know, are pouring tremendous energy into this. I brought them back to Santa Barbara in 2019, and here we are in 2020. Of course, the pandemic is, with everything, thrown a little bit of a wrench into our works. We had basically one in-group meeting last summer on the top of Mount Royal in Montreal, but most of our meetings now all over Zoom. Okay, so I'll just mention a couple of problems we're working on. I won't go into a lot of details. If you want, I'll be happy to stick around, you know, after my talk is over and go into these. But I mentioned them, you know, this idea of what's the stability of the sail under the laser loading, what might happen when those dust grain impacts. And then I also have a group of students looking at maybe a more near-term application of the phased array laser, which is something called laser thermal propulsion. It won't get us to the stars, but it's a fantastic technology for getting around the solar system quickly. So I'll just show a couple slides here. You know, ideally we want the sail when the laser is acting out to look like this, but how do we know it doesn't look like this or look like this? So I've had a student, Dan Cornelius Savu, who's just finished a wonderful honors thesis. We're working on getting this polished up now for a journal publication, of looking at, if you do what we call normal mode stability analysis, you put a wrinkle, a sinusoidal wrinkle in your sail, does it flatten itself back out, or does it wrinkle up even worse? So he's developed a nice analytic theory for this, and we have an analytic expression now for what we think is the Young's modulus we would need on the sail, or the tension that we would need to keep in the sail. Maybe we need some kind of inflatable ring or something to keep the sail pulled, you know, taut, like a sail on a ship. And he's also done a full finite element analysis of this, all derived from Lagrangian dynamics. So I'm very gifted to have a student like Dan Cornelius, who loves doing Lagrangian dynamics, and developed a complete Lagrangian treatment of this. And it looks like our analytic theory and our numerical simulations are matching. And we basically now think we have a theory for what properties of a sail you would need so that it doesn't get crumbled up. The next thing I mentioned was the dust grain impacts. So this is a problem that I've had a student, John Kokalis, working on, and I've had another student I recruited from physics, an undergraduate named Monica Asmenskov, who's a physics student that we needed help with the optics. So again, most of my mechanical aerospace background, not that relevant to a lot of these problems. And I had forgotten all of my undergraduate optics. So we had Monica, sort of reteach us all of the Rayleigh criterion and diffraction and edge diffraction and so on that we needed for this project. But yeah, the idea is is if you look at a square centimeter of a sail, as it's during that acceleration phase in the solar system, for those 3 minutes when the laser is pushing on it, it's going to get sort of peppered with little impacts of dust grains. And that could be bad, and particularly if they affect the sail's ability to not absorb the light. If they start to damage the sail and it starts to absorb the light, that could be a real problem. You can actually have phenomena called fiber fuse, where a fiber optic starts to absorb laser light, and then that damage starts to grow. And it can even happen in sort of a detonation mode. There's something has a very unfortunate acronym called LSD, but it's called laser supported detonation, where a laser starts to couple to damage and it would just spread out and maybe within milliseconds just vaporize the whole sail. So what John and Monica have looked at is there a way we can use that big laser to maybe vaporize the dust grains ahead of the sail? And it turns out that the sail will likely be partially transparent. Okay, if you optimize it for acceleration, it is actually better off to have the sail a little bit transparent and let a lot of the photons through. And what John's calculations have shown, just using a simple energy balance and an ablation model, that as these dust grains get closer and closer to the sail, so here's the sail here, here's the dust grains coming in from the sail's point of view, they're coming in at 20% the speed of light. While the laser is on, we might be able to vaporize them before they get to the sail, and that might save the sail. Now, when the laser's off, we can turn the spacecraft edge on, and hopefully we'll get fewer impacts that way, and maybe you can have some shielding on the front edge of the sail when it's in the coast phase for the 20 years where it's just coasting through the interstellar medium. But it's really during when the laser's on, we want to try to mitigate the effect of those dust particles hitting the sail. And then finally, I'll just show one slide about this. I can't do full justice to this because I have a large crew of students working on this now, but we're looking at using the UC Santa Barbara laser technology to get around the solar system more quickly. And if you're doing missions within the solar system with velocities on the order of 10 to 20 kilometers per second, you're actually better off using a reaction mass to couple the laser. Okay, so when you want to go to the stars, forget about using any kind of rocket, even fusion rockets, as I mentioned earlier, very, very hard to get to the stars with. But for getting around the solar system, essentially rockets are still the way to go. And if you can have a big inflatable mirror attached to your spacecraft, you can, again, receive that laser flux and focus it into a heating chamber, expand that through a nozzle and generate thrust. And it is almost as good as a fusion rocket, but without the fusion reactor. Or it's actually quite comparable to something called nuclear thermal rockets, but again, without the nuclear reactor. So Zhofeng Bao, who's I think on the Zoom here with us, just finished a very detailed honors thesis where he did a modeling of that laser-supported plasma inside the engine, which interestingly is very, very similar to sort of combustion waves and detonation waves. So amazingly, I decided to launch out and go to the stars, but often you find yourself passing back through areas of expertise that you already had here as well. And then I have a student just graduated from McGill named Emmanuel Duplay, who, in addition to being a very good engineer, is also a wonderful graphic artist, is doing all these beautiful renders you're seeing. And he led a whole team of students last summer, since because of the pandemic, we couldn't get into the lab. He organized a team of about 8 students that did a complete design of a Mars mission using this laser thermal rocket, and basically showed we could get to Mars in about a month rather than using the usual 6-month trajectories to get to Mars we do now. And we had a wonderful again, using Zoom and just opening it up on social media, we had a design review meeting last August that was wonderful. We had people from aerospace industry and people from academia and so on just come on. Some people, total strangers, came on and gave us all kinds of wonderful feedback on this design that we're also now writing up. So yeah, just to conclude, I want to say a bit about how you build a community. So I'm not the only person interested in interstellar flight. There is about a half a dozen organizations out there, all looking at trying to develop not just the technology, but also prepare society for how we could do this. How could we make, like the 20th century was the space age, how can we make the 21st century the interstellar age, or the century of the starship, which you can see here. I'd encourage you to look into all these organizations, and a really wonderful resource I'll mention is there's a blog called Centauri Dreams. It's run by a journalist named Paul Gilster, who wrote a book on interstellar flight about 15 years ago and maintains this just wonderfully curated blog where he basically tracks all the developments going on in the interstellar community. So if you're at all interested in this, I really encourage you to just follow this blog, and it will keep you up to date with what's going on in all these different workshops and meetings. Again, this is my tribe now. All of these people are my friends and colleagues. The kind of the challenge, though, is a lot of these people are amateurs, and I say that out of just total respect and admiration. You know, they're people that do this on their spare time, people that are maybe retired from national labs or from industry that have, like me, had this interest all their life but could never engage it. The thing think we need to get to is, in order for me and other academics to work on this problem, is we need to start building a real research community that publishes papers, that starts to build up citations, because that is in academia sort of how we're evaluated, how we're judged. That's how, at least in Canada, how all of my grant applications are often evaluated, is they look at my prior research, and those of you that are academics, you know the game. It's counting up the citations, right? And so I've had to explain this to some people in the interstellar community, all of us, you know, who are interstellar enthusiasts, you know, all of us are here because of Robert L. Forward. Forward, unfortunately, passed away relatively young. He developed a brain tumor and died. I remember seeing him in, I think, 2000, 2001 was the last time I had a chance to interact with him, and really, really sad we lost him young. But I often have to tell this to people in the interstellar community who, like me, revere Robert L. Forward. I have to tell them that as amazing as Forward did at work, you know, just incredibly innovative ideas, if you were to look him up on Scopus, you know, his H-index is really not that impressive. That's probably not impressive enough to these days to get tenure at a top-tier university, okay? And certainly in the peak of his career, you know, his number of citations were counted in the dozens, okay? And it's just because there weren't enough other people doing work on interstellar flight for his work to sort of rack up the citations that it deserves, okay? So this is what I've, kind of my message to people who are interstellar enthusiasts. There's a famous quote that comes from a movie called The Right Stuff. This is the old movie from the 1980s. I think there's a new series based off Tom Wolfe's The Right Stuff, but this comes from the movie in the 1980s, which is talking about the early space race in the 1960s. And the quote is, "No Bucks, no Buck Rogers." Okay, so if you don't know who Buck Rogers was, he was originally a comic strip, cartoon character, and then a movie, and then a television show that for decades was associated with being a spaceman. Okay, to be in the shiny spacesuit and to go out in your rocket ship meant you were Buck Rogers. And usually what the quote really means is it's the other way around, is that if you want to engage the public in space flight, you need to have astronauts. You need to engage them with the excitement of actually launching people into space. So I think I'll put in the chat, if you don't know this quote, I think I'll put the little movie clip here in the chat. You can watch this so you understand what the quote is. So you can watch that at your leisure. But to get back to my talk, well, I've given away the punchline here. But my version of this quote is, no citations, no starships, Okay, and you know the game. If you're a graduate student or a postdoc, and all of this is very recent. Okay, when I was a graduate student, I don't think I knew what any of these terms meant. Okay, I mean the H-index is a relatively recent thing. Jorge Hirsch wrote the paper on the H-index in 2005. You know, this is all very, very recent. This sort of infometric craziness that we live with, where everyone is evaluated on how many citations they rack up. And I think this is had it's had a very significant way that young researchers approach what research they're going to do. I'm not going to say if it's good or bad. I think that's the discussion I'd like to have with everybody today. But I mean, when I was an undergraduate thinking about going to graduate school, I was thinking, where can I go to do cool research? And I ended up going to Seattle, University of Washington, Seattle, and working with another very innovative gentleman named Abe Hertzberg, more or less because Abe Hertzberg was friends with Robert L. Forward. And Robert L. Forward had actually retired in the Seattle area. And the idea that I could maybe meet up with Robert L. Forward a couple times a year when he would come on campus had an enormous influence on me. And I wasn't thinking about any of these issues. Okay, so this is kind of the choice I have faced, and this is the choice I think many of you may be facing in your careers. I mean, I sort of had to decide in the last couple of years which one of these mountains did I want to sit on top of. You know, I was an editor of a journal, 2 journals, and I know a lot about publishing, and I can do an awful lot to sort of help students rack up their citations. And the way you do that is by publishing in a field where a lot of other people are publishing. Okay, but if you really want to do something very innovative, like helping me figure out how we're going to get to the stars, you're not going to be racking up a lot of citations, and you're going to have to maybe struggle to draw in serious researchers and serious academics. Okay, so again, returning to this, you know, this slide, what can we do to give people the freedom to do the research that they really want to do what they dreamed about when maybe you were, you know, I was 17, 18 years old reading Robert L. Forward's novels, and not have to wait 30 years or 40 years till you're over here and you finally have the freedom to do what you want. So I think with that, well, let me just maybe say one other thing. You always have to kind of temper that with this idea that when you're on one mountaintop looking over at another mountaintop, often it looks better on the other mountaintop. So, you know, there was many 2 decades of my career when I was working in kind of mainstream combustion with Xiaoqian and so on, and going to big conferences where we had you know, a half a dozen journals we could publish in, and you were sort of confident that if you published something, someone else that was working on the same problem would be publishing papers. And I was looking at other, you know, I would be in that world looking at these innovative researchers like Philip Lubin, Mason Peck, that were talking about interstellar flight, and I say, oh, you know, they have it better off. They're in this virgin field where the problems are wide open. But then you go over to that other field, and then you start to look back at the field you left, and you say, you know, I kind of miss having a community. I kind of miss having a large community of other researchers that I could, for example, send a graduate student to go and do a postdoc with, or I could get a postdoc from their group. Okay, so this saying, if you don't know this, the grass is always greener on the other side, is for me, when I'm in a well-developed field with a lot of research going on, the idea of going to a less developed field where there's fewer researchers looks appealing. But then when you go to that side of the fence and look back, you know, the grass was greener on the side I left from. So if you don't know this, I was doing some research last night to see if I could find a cultural equivalent to this. So apparently in China, the expression is, you know, one mountaintop looks taller than the other mountain, regardless of which mountain that you're standing on. So I think these are the kind of things I'd like to discuss with you. If anybody wants more details about interstellar flight, I'll be happy to talk about that for a long time. But I think for you know, the other Martlet Society presentations I've seen really raised some I think interesting points about research. What's the proper role of research? And so I think these are kind of the talking points I would enjoy engaging with everyone. So I think with that, I'll stop and open it up for any questions people might have.
Yeah, thanks so much, Andrew. Yeah. So I think we have some questions, but Xiaocheng will lead the QA section. So
Okay. Okay, fine. Yeah, we got some questions from the QA chat. Okay, so I will ask. I think most of them have already been promoted to the panelist session, right? I would maybe, if they want, they can just unmute themselves to ask directly. I see Dr. Bill Higgins has a comment. I wonder if he wants to just talk directly.
Yeah, please, Bill, go ahead, unmute yourself.
Yeah, yeah.
Okay. I just made a remark when you were talking about, when you were showing us the long list of the Breakthrough Institute's problems, which I thought for them was a great way to address all the people that might be potentially interested in this. The problem that I instantly noted when I heard about what their plans were since I worked in particle accelerators all my life is, gee whiz, what happens to interstellar hydrogen when the speeding spacecraft collides with it, which is analogous to the dust problem that attracted you, but on a much smaller scale. And the answer is it's like flying through the beam of a 20 MeV particle accelerator.
It is, yeah.
Yeah. So like everybody's, the idea that there's a list of problems and everybody can focus in on, so, hey, I know something about that, or begin to wonder, or start to take out their slide rule and start working on some of these issues is a way of drawing in people who are already interested in this stuff.
Yeah.
I guess the other thing I wanted to say was that the final problem you address is it's really interesting to see that in a talk on interstellar flight or some kind of space propulsion, and if you can form a disciplinary community with people talking to each other, conferences, journals, and so forth, growing that from a little seed is a problem that I think one needs to think about whatever research one is engaged in.
Yeah, thanks, Bill, for the comments. I just want to introduce Bill here. So Bill Higgins is actually no relation to me, even though we have the same last name, but he's a physicist that works at the Fermilab National Accelerator Laboratory near Chicago. And I'm really honored to have Bill here because Bill is one of the few people that remember me from back when I was 18 years old. So he and I knew each other through what used to be called the L5 Society, then became the National Space Society. It's a grassroots space advocacy organization. And Bill remembers me back when I was an undergraduate just dreaming about this stuff before I became sort of a mainstream academic. So it's great having you here, Bill. Yeah, so Bill's absolutely right. That there's another big problem is not just the dust grains, but the interstellar media. Even when you're out between the stars, there's about every 10 cubic centimeters, there's going to be a hydrogen molecule. And yeah, when those things impact you at those speeds, it is going to be gigarads of radiation you're going to be exposed to. So that's a problem we're aware of, we need to work on. Philip Lubin's doing a little bit of work with that. He's engaging people from the high energy physics community to look at that problem. And so it's going to involve probably having a lot of redundancy in this chip, that wafer sat I showed you. I mean, kind of the vision, I think, is that the whole sail would probably have a massively paralleled, neural networked, whatever, dream up whatever you want, chip integrated into it. And so different areas can be damaged and it can just work around those with a lot of redundancy and backup. We've actually, when I was there in 2019, he was actually working with some scientists from Italy that could actually maybe do some testing, in facilities that can actually expose the little chipsat to the kind of fluxes they might see. So yeah, it's no shortage of good problems to work on. And again, it's the appeal that this field has to me is when you're on one side of that fence that I'm showing, when you're in the large community there, if you want to make a contribution, you have to get very, very specialized, and you really have to work very hard to be a master of a very narrow domain. But when you go into a new field, like interstellar flight, there you don't need to be the world's authority to make a contribution. If you know a little bit, you probably know more than anybody else that's working in the interstellar community, because it's right now such a small community. So, when I showed that problem we did this summer on the stability of the light sail, I'm actually not a deformable solids person. I hadn't opened my copy of Timoshenko in decades, but I knew from talking to other people in the interstellar community that nobody else was working on that problem. So that was something we were able to make a contribution by not being, just so hyper specialized. Yeah. Okay. So Zhao Chen, I think maybe.
Yeah.
Go to the next question.
Yeah, there is a second question from Tarek Lee. Tarek, would you want to just ask it directly? Unmute yourself.
Hi, Professor Higgins. Thanks for the talk. That was very interesting. So you mentioned that there's a design for a starship that travels within the solar system that uses the laser as a power source. So I'm thinking, in this case, what type of propellant are you thinking of using for this ship?
Yeah. So this would be not quite a starship, because it's not gonna go to the stars. That's the one thing. A little miffed about Elon Musk calling his new vehicle a starship, because it's not going to actually go to a stars. But this would be this design that Emmanuel and his team came up with. I'm showing here. Would get you to Mars. You see sort of a reentry capsule at one end there that would get you to Mars. So to answer your question, the propellant would be, in this case, hydrogen. So if you're able to decouple the energy source from the reaction mass, in that case, you want to use the lowest molecular weight reaction mass you can. So you would want to use hydrogen, which is the lowest molecular weight substance we know of. And it's very similar to a concept I mentioned called nuclear thermal rocket. So these actually were developed very extensively in the 1960s under something called Project NERVA. In fact, the technology was so mature, had the Apollo program gone on, my colleague Jeff Grayson makes this point, had there been an Apollo 20, it very likely could have had a nuclear thermal rocket on board, basically a nuclear reactor that you would use to heat hydrogen to very high temperatures, 3,000, 4,000 degrees, and then just expand that through a nozzle. And with that, you can get a specific impulse of about 800 to 1,000 seconds. That's a measure of how much thrust you get out of the propellant. That's about twice what we can get with chemical rockets right now, which is great. So a lot of interest in this really since the 1960s till now. Just the concern is you would need to deliver a full nuclear reactor to space. And there's likely going to be a lot of concern about doing that because of possibility of accidents. Well, the laser thermal propulsion, the concept we were working on, can essentially get you that same performance or maybe even better. It's almost as good as something called a gas core nuclear thermal reactor rocket, where you can get to temperatures of almost 10,000 degrees and you can get ISPs of maybe 2,000 or 3,000 seconds, and you don't need the nuclear reactor. It's a nuclear-free technology. The only issue is that you can only reach so far out into space with that laser. So the design we looked at this summer was we had a 10-meter diameter laser, and we could get the laser out to distances of about the moon. So we would just do a really hard burn early on and throw that vehicle out of near Earth space towards Mars, and it would coast most of the way there. But if you could then build them, a laser on Mars and elsewhere in the solar system, you could actually use this like a whole transportation infrastructure to get around the solar system quickly. Okay, but all this really enabled by the laser, by the development of these inexpensive fiber optic lasers that we can stack up and build a giant laser the same way now that we stack up a graphics card to build a supercomputer.
Yeah. We have another question, like this from this colleague. I didn't get the full name. He wrote in chat. He said, like, will anisotropic emission of photon affect the Earth's orbit?
Okay, so there is some interesting effects that happen when objects emit thermal emission of photons. So I'm not an expert on this, but if you have really small things like dust orbiting the sun, or you have little pebbles, dust grains, small asteroids, there's a number of effects. Robertson pointing effect, there's something called the Janowski effect, the Yorp effect. And so there, when objects interact with radiation from the sun and they re-emit photons, it has a small effect on them. It's a very, very small effect, but over years and years, it can affect the orbits of small things, things that have, you know, a large surface to area ratio. So dust grains and little pebbles and so on. Objects that are on the size of planets, my understanding is they're not affected really by the radiation pressure at all. You know, they're affected by perturbations of other planets and so on. But for something as big as the Earth, the radiation that is hitting it from the sun and the radiation it re-emits doesn't affect it really at all. But it's interesting, you know, I was an aerospace engineering student. I studied orbital mechanics, and there all you learn is just classic, you know, Newtonian mechanics or Hamiltonian dynamics, and you don't learn much about these other effects. And then I've always kind of been interested in astronomy, and you know, over the years when I would read about you know, dust physics and so on, when I was in grad school, I knew a graduate student named Stan Love, who worked with Professor Brownlee at the University of Washington that later did the Stardust mission, where they went out and actually recovered grains of dust and studied those. And Stan Love later became a shuttle astronaut. And you know, we read their papers, it's all about these effects that radiation absorption re-emission has on the lifetime of dust and how its orbital dynamics is and so on. But I never knew anything about these. And I was always curious, like, why don't we learn about those in spacecraft engineering? And I'll just give a shout out here to Mason Peck at Cornell, who wrote a really beautiful paper about 10 years ago. I think the first author's name was Atchison, one of his graduate students, wrote a really beautiful paper where they looked at all of the forces that can act on a spacecraft. So perturbations due to other planets, radiation pressure, this Janowski effect, Robertson pointing effect, and they showed how they change as you scale spacecraft size. And for normal size spacecraft, these effects are negligible, but when we get to these little tiny chipsats and so on, these effects start to actually be significant. And that paper was a real revelation to me, because I finally understood, you know, why is it you worry about these things for dust grains, but not for larger spacecraft. So that's a great, if you want to learn more about, you know, how these different effects scale with different sizes and so on, that's a wonderful paper from Mason Peck's group.
Okay, great. And the next question is actually from one of our new friends made from our destination forum. It's from Jorge Diaz. He asked, do you or the community have any crazy thought on interstellar travel for humans?
So actually we do. So there's a whole bunch of other ideas out there that I just, in just the time I couldn't go into today. So if you want to bring humans to the stars, you could do it with a sail. Only now you need to find a way to lower the accelerations and keep the laser focused for a longer distance. There's some very exciting ideas out there about we might do this now. I just want to mention one researcher that is doing some work that has me very excited. His name is Chris Lembach. He's at Texas A&M, and it's exciting to me. Another reason, he kind of comes out of our community. He's a sort of a laser plasma diagnostics person that comes from reactive flows, kind of from the same community that Xiaochen and I are from. But he has an idea that you might be able to couple a laser to a stream of particles. So if you can have lasers interact with particles, the laser beam can help move the particles in, and the particles can also help keep the laser focused. So it would be a coupled particle stream, laser stream. And he calls this concept Proxima. He has funding from NASA to look at this now. And that would be very interesting, because then you wouldn't have to worry about the laser beam spreading out. You could keep the laser beam collimated out to possibly interstellar distances. So now you can keep pushing on your spacecraft and keep slowly building up acceleration. So that's one idea, very exciting, worth looking into. There's another idea that Robert L. Forward worked on. Before he did his light cell work, he actually looked at antimatter. Could we do something right from Star Trek, which is use matter-antimatter reaction as a fuel for a rocket? And that is a way you could get to the stars using a rocket. Just the bottleneck there is how do we get the antimatter? And right now we do have factories that make antimatter. One of them is where Bill Higgins works at Fermilab. Just the problem is the quantities of antimatter they make now, they count them antiproton by antiproton. And to get to the kilogram quantities we need is a real scaling problem. But there's people working on that. So there's some of Bill's former colleagues from Fermilab have a company now, again with funding from NASA, where they're looking at how we might be able to scale up antimatter production and actually use antimatter rockets to get to the stars. And then you can decelerate, because now you've got your energy source on board with you. So when you get to Proxima Centauri or wherever you're going, you can flip around and do a burn and decelerate. And then there's even a few more far out ideas. I'll mention I'm exploring some ideas in collaboration with Jeff Grayson, who's with the Tau Zero Foundation, one of these other interstellar foundations, looking at, is there ways we can interact with the solar wind and the interplanetary and interstellar media? So there is stuff out there I mentioned, and rather than being a liability, is there some way we could interact with that media and use it as a kind of perhaps reaction mass, or maybe as a kind of wind that we could surf on or soar on to get to the velocities we need for interstellar flight? Right now, these ideas are so vague, we don't even have renders of what they might look like. But it's fun because it's this totally new ideas. Like Jeff Grayson says, if you're an interstellar enthusiast, right now it's 1903. Okay, it's like we're the Wright brothers playing with aviation for the first time. So kind of the field is wide open for someone like, I always look sort of like Theodor von Karman as my hero. When these early aviation pioneers started to play, they would just build ideas, try them, sketch them out, but there was not a lot of serious engineering analysis on it, So we sort of had our Tsiolkovsky, and we've had our Goddard, and we've had our Hermann Oberth for interstellar flight. That's who Robert L. Forward is. Now is the time that we need people like Theodor von Karman that come in and build, sort of the great schools of aeronautics and astronautics that will develop these technologies with the kind of rigor that we're used to in serious scholarly work. So yeah, there's ideas out there. People are looking also, hibernation. Can you put people in cryo sleep and maybe do the slow boat to Alpha Centauri? So yeah, all these ideas are out there, but I like to think about doing the robotic missions first, because it's almost certainly going to be the first thing that we'll do. I think like a lot of you, I'm a science fiction fan, and when you read old science fiction from the 1940s and 50s, they always envisioned, well, we'll go and build a space station in orbit, and then from there we'll build these great interplanetary ships, and we'll go and explore and colonize Venus and Mars and so on. But if you looked at how it actually happened, I just was looking at the dates on this. Our first missions to Venus and Mars were launched in 1964. Okay, the Mariner spacecraft were launched just 5 or 6 years after Sputnik. So once it just barely became possible to put things into space, right away we were launching robotic missions off to the planets. And the human missions, we're still waiting for those, And I think it will be that way with going to the stars. I think that as soon as it's technologically feasible, once we have a design, and right now I think this Philip Lubin breakthrough starshot architecture should be our plan A. Once that looks like it might be feasible and we can get the cost of it comparable to something like a Fermilab or a Large Hadron Collider, then I think it's just going to happen. Just like, throwing a very primitive robotic spacecraft on top of an intercontinental missile, which is what the early, Sputnik and Atlas and Titan rockets were. They were intercontinental missiles, and just throwing them out to the planets and do flybys and send pictures back is going to be the first thing that will happen. And then humans going to the stars, that's going to be, I think Star Trek had it right. I think that's going to be 23rd century technology. But, we can certainly start thinking about it now.
Yeah. So the next question, I think you has already answered partly, is from Mohammed Saif. He said, once the ship is further away from the laser coverage, how is it going to steer or brake?
That's an interesting problem. I think that's on the list of
yeah.
those problems we need to work on. But it will probably have to have some form of propulsion on board. So once the laser's off after 3 minutes, that's it. The laser's done its job. We actually can use the laser to launch another probe and another probe and another probe. If it only takes a couple of minutes of laser power, there's no reason why we can't launch one a day and just shotgun these out to the stars. But yeah, when it's now in the coast phase, just like when we do the missions to Voyager, to Jupiter, Saturn, Uranus, Neptune, or New Horizons, those big rockets give it the early delta V, the early large velocity change it needs. And then from then on, it's just very minute course corrections that are measured in not kilometers per second, but meters per second. Okay, and that's probably the kind of little tiny course corrections we'll need. And so you can imagine you'd have some energy source on board. You probably still have a little tiny nuclear battery on board. You can use that to maybe run a little tiny ion engine. Maybe you have a little tiny photon thruster, a little tiny laser that just using, again, photon pressure can just do the tiny, sort of attitude control and pointing that we need. There's also a weak magnetic field in the galaxy. So maybe you could deploy kind of a loop of superconducting wire and use that to do little course corrections, interact with the magnetic field to steer the spacecraft. So those are good problems. Those are on the list. I think people are working on those. Jeff Landis, Phil Lubin, I know, has done some work looking at these problems. For me, it's lower down on the list. I mean, for me, I kind of like the interstellar problem because doing that main propulsion, getting up to we need to get to 60,000 kilometers a second to get to the stars, right? I showed you that hypervelocity launcher we developed at McGill 10 years ago, and we got to 12 kilometers a second with that. It's the fastest, launcher, fastest gun in the world, but it only goes 12 kilometers a second. We need to get to 60,000 kilometers a second to get to the stars. We need several more zeros. So that's a really hard problem. And so if you like to think about, gosh, what's a really, really hard problem I can just focus all my energy onto, that's a good one to think about. So that's what I like to spend my time thinking about.
Yeah, another question from Nathan Macklin Max. He asked about that. Are there any realistic applications of self-healing materials that could be used on the solar cells?
Yeah. I think it would probably need to be some kind of intelligent self-healing material. This idea of self-healing composites, that was actually an old professor of mine from Illinois, Scott White, did the early work on this. Can you have a self-healing material? An interesting thing from my work with General Fusion is there's their concept for a fusion reactor actually has the inside of the reactor being made out of liquid metal, liquid lithium lead, to shield the rest of the reactor from the neutrons that come out of the fusion reaction. And this is some discussions I've had with Phil Lubin. Maybe we could have some similar idea. Maybe the leading edge of the spacecraft would be some kind of liquid metal that would be continuously circulating. And so it would absorb all the flux of those mega electron volt protons that we were talking about. And if something gets damaged, there's a dust grain impact or something, you could have a continuously replenished leading edge of the sail. But we're not going to do this, it's not going to be tomorrow. I think what is good to think about is there's a lot of technologies that are developing for other applications. And Yuri Milner, who's put in the $100 million into this Breakthrough Starshot Initiative, I think he wants to do this. I forget if he wants to launch in 2061 or he wants to get the pictures back in 2061. But he was born in 1961, the same year of Yuri Gagarin's flight. And he was named after Yuri Gagarin, being born in Russia. It's where his name Yuri Milner comes from. And so he's thinking 2061 is the year. There's another individual, he's out of power now, but there was a congressman from Texas named John Culberson who was pushing NASA very, very hard to make a commitment to do a mission by 2069. So he felt that by the 100-year centennial of the Apollo landing, we should have pictures back from another solar system by the year 2069. So these are kind of the timescales we're thinking about. And that's why partly why I'm working with a lot of undergraduate students is we need to get young people involved in this for the long haul. I kind of like the year 2069. I will be 99 years old in 2069. So if I keep healthy, keep working out, keep taking my omega-3 tablets every day, you know, I could be there for the launch or when we get the first pictures back. But I think there's going to be a lot of technology development in terms of, you know, flexible electronics, photonics. You know, people are talking about making an entirely photonic computer now. Well, that would be nice because that photonic computer could be integrated into the photonic light sail. That would likely be the architecture that we'll use. So, you know, that's an interesting thing. That's really what I attribute Philip Lubin's thinking is look for technologies that are undergoing exponential evolutions and then think about how we could repurpose those technologies, like all the incredible technology that's going into our smartphone. How can we repurpose that to do these just incredible missions that would be unconceivable 30 or 40 years ago?
Yeah, actually, there is a comment, but I don't see the person who posted the comment still in the list. So probably for the sake of time, we'll skip this one. And there's another question from Xuan Li, but I think his question is similar to what Mohammed Saeed's question previously is about like how to steer the spacecraft, and so perhaps for the sake of time, I will also skip this one. And now we have here William Georges has a question, and I think it's interesting. And Will, if he wants, he can unmute himself. I think he's already in the panelist list.
Yes, hello. So my question is, the way I understand it is multiple light sails will be accelerated towards the same target. So we wouldn't launch only one. I'm just wondering, since you're going from, let's say, the Sun to Proxima Centauri, would the laser light from launching a second sail affect the trajectory of the first sail? Like, has anyone thought about that, or is that just not an issue?
That's a good question. You know, I don't know. Yeah, I mean, I guess they would be lined up in the same direction, but the real expert is actually on the Zoom here with us. So my honors student, John Kokalis, just finished his honors thesis on this in December. It turns out, I think once you're past the focal point of the laser spreads out really, really fast. And that's what we were looking at for this, could we use the laser to vaporize some of the dust grains? I think, 24 hours later, when you go to do the next launch, the spacecraft is going to be so far away, the sail is going to be so far away. I think by the time the laser gets there, it'll be so diffused out that I don't think it would have much of an effect, but probably want to do that calculation pretty carefully. To make sure. Actually, Phil Lubin wrote a paper. I helped them a little bit when I was there on my sabbatical. This is one thing I was able to help them with, is they looked at, what's the probability when you're doing this laser operation that you might hit a satellite that's in orbit? And it turns out the odds are actually very, very low. Okay, so space is big, even low Earth orbit, near Earth space, we hear about the orbital debris problem and so on, but if you just shine a laser up for 10 minutes, your odds of hitting it's like 1 in a million. And then if we have a database of all the satellites that are up there. Bill and I, our friend Jonathan McDowell, he could advise us. Actually, I brought Jonathan in on that paper a little bit, just to advise us that there's a database of where all the satellites are at. So you can pretty make sure your laser's not gonna hit them.
Yeah. Yeah, another just quick question. I think it's also like a comment. Is from Kartik, and it says, any thought on the intergalactic travel, impossible even after being an interstellar species?
Okay, so this is interesting.
Yeah.
So, so this is I'll tease you with the puzzle here. So, I talked about that scale model of the solar system, right? Where the solar system was about the size of a university campus, and then the nearest star would be 4,000 kilometers away at the Panama Canal. So there's another one that you can do is if you shrink down our solar system, like the orbit of Neptune, down to the size of a quarter, a coin. Okay, how far away is the nearest solar system? So really shrink the model down, and I think it turns out I forget, it's on the order of kilometers or miles. I think if your solar system is the size of a quarter, the nearest solar system is still far away. But what if we took our galaxy, the Milky Way galaxy, and shrank the entire Milky Way galaxy down to the size of a quarter. The nearest galaxy to ours is the Andromeda galaxy. It's also about the same size, about the size of a quarter. How far away do you think that other quarter would be? So Milky Way galaxy, 25-cent coin. Andromeda galaxy, 25-cent coin. Does anyone want to take a guess how far away the Andromeda galaxy is? Somebody's got a guess. I'm not going to give you an answer.
Yeah, someone said like millions of kilometers or on the moon.
Okay, the answer is about 5 centimeters, about 2 inches. Okay, if this is our galaxy, the Andromeda galaxy is actually right here. Okay, so galaxies are actually quite close together. And Andromeda is actually going to hit our galaxy, I think, in 1 billion years or so. We're actually on a collision course. Okay, so it turns out galaxies are actually quite close together. The big, if you sort of look on a log scale, the most empty regions of space is interstellar space. So the distance between the stars is enormous. But if you sort of zoom out and look at our whole galaxy, you know, this island of stars that we live in, the other galaxy is not that far away. Okay, so Andromeda, I think, is on the order of, I don't know, 1 million light years away. Okay, and if you're an amateur astronomer, you know this, because the Andromeda galaxy, you have to be in very, very dark conditions to do it. If you see it, it's actually a big smudge in the sky. You can't even see it with the normal telescope. You're better off with your naked eye because it's so big. It's hard to get to another galaxy, but it's actually not that much harder than interstellar flight. So if we were to develop something, this is what kind of Star Trek gets wrong, is if we had a warp drive that we could get from star to star within, I don't know, in Star Trek, what does it take? It looks like to me days or weeks to get from star to star, or to get across our galaxy. I think in Star Trek Voyager, it took them a couple years, right? But if you had that technology, to get to another galaxy is actually feasible. It actually would take you, maybe 10 times longer to get to the next galaxy, but it's not, it's not millions and millions of times harder than getting to the stars. So that's kind of counterintuitive. There's a great, maybe I'll just share one more thing with you here, is there's this fantastic, it's been done many times, but I'm a big fan of the original. And I always start when I recruit new students to my group, we always watch this. It's the Philip Morrison's Powers of 10 movie, which I'll put in the chat here. Is just a fantastic visualization of this. And you'll really see this when you play this little movie, that the really boring part, actually the most boring part, if you start at quarks and, go up through the nucleus of the atom and so on, through DNA, through cells, through our bodies, through our solar system, then to the stars, our galaxy, the local group of galaxies, and so on. The most boring part of that movie is when you go to, is going from our solar system to the next solar system. There's just orders and orders of magnitude. You sit there and wait to go by, and really nothing's happening. But then when you get on the scale of galaxies, you start to see all kinds of galaxies. They're you've probably seen these incredible Hubble Space Telescope, deep field images where they just take the Hubble telescope and point it at a point in space and just collect light for 2 weeks. And what you get at the end of that is just smatterings of galaxies everywhere. Okay, so yeah, it's interesting. Galaxies are close together, but it's the stars within the galaxy that are very far apart.
So if you don't mind, actually I think there are 2 more questions. One from the list, and I think our host Jen also has a question. So this one is actually from Mohammed, which I don't know his last name here. It doesn't display. He said, regarding academics metrics, what do you recommend to change their impact on the role of getting funding and building new communities?
Yeah, so really it comes down to, and this is what I have out on my desktop here this morning. I have with my students, with John and Xiofan and Emmanuel and the other students that are on the call here. We're working on four papers we're trying to get out this winter. Probably I should listen to my own advice and just get these papers finished up and published. But I'm trying to get the other members of the interstellar community to keep publishing and so on. And it's, again, I have to use a quote from a movie here. It's if you build it, they will come. Okay, so if you start building up enough publications on something, you will start to attract, I think, academics to it. It's just, we're going to have to be patient. It's going to take a long time. And I sort of have seen this over my career in aerospace and in propulsion, detonation, these fields I've worked in, that once you start to build up a critical mass of papers around something, people start to say, well, there must be something here and we should work on that. I mean, I think, Xiaoqian, you and I have seen that on, kind of rotating detonation engine concepts, our work on discrete detonation now. If you just start to publish enough papers on something, you build up this critical mass, and then other researchers will say, hey, there must be something to this. I see a lot of papers coming out on this now. This is something new, and they'll be drawn to work in this field. And you will build up that critical mass, and then the work gets better and better. And, I didn't want to, I want to be careful that I don't want to, I'm not at all sort of insulting this individual on the right here. Okay, so I have the highest respect for my fellow academics that sit on top of their hill of expertise and train students and get them to publish a lot of papers and drive up citations, because it's actually excellent work that comes out. The system works. I think had you invited me, maybe 15 or 20 years ago, I was kind of in a bitter period of my career where I said, all these citations and stuff, it's all just people scratching each other's backs and patting each other on the back. And the good work, or probably what I was thinking about, was my work is not getting cited very much. But if you're patient, and in academia, patience means on a time scale of a decade or more, you will start to, the good work does win out, and I've seen the excellent work that, maybe not my work, but my colleagues' work, people of my cohort and even younger, I've seen the really good papers start to rack up the citations, and other people start to build work around those. So it takes time, but you got to have a community. You got to have a lot of people publishing to sort of drive the field forward. But when you're over here working on something as esoteric as interstellar flight, it's going to take a long time to build up that community. But we've got to do it. So people that work in this, we've got to publish. There is one journal that's kind of the main outlet for this. It's a journal that Bill Higgins knows very well. It's called the Journal of the British Interplanetary Society. It's actually the oldest continuously published journal in astronautics. Dates back to the early 1930s. And it's where Robert Forward published a lot of his work. It's where a lot of us now publish our work in interstellar flight. But just to sort of show you how crazy things have gotten, that journal actually lost, it's a real tragedy, but it lost its impact factor. So there was a lot of delays with the journal. They were having trouble getting out the issues in time. Its impact factor was dropping. And Thomson Reuters, who publishes the impact factor, basically delisted it. And that means if we publish in that journal now, as a professor, your publications don't really count. They don't really contribute towards your H index. And that was really, really sad, because it's a wonderful journal. It's what I was, as an undergraduate, reading all these papers in. But I think it's a symptom of what's happened. And what I worry is that it's driving young researchers to actually be more and more conservative, right? So if you want to rack up your H index, the best thing for you to do is to publish in a field where a lot of other people are publishing, okay? If you work in kind of very prosaic mainstream research, there's 20 other people working on the same problem you are, and that means, when they publish the next paper, they're probably going to do the literature review and cite your paper. And so you're going to rack up 20 citations. And that's sometimes what you need to do to advance your career. So I think that's the conundrum. That's the dilemma we have to solve, is both of these mountaintops are important. And, I've kind of, over my career, been drawn back and forth between the two of these. The grass is always, wherever I'm at, the grass always looks greener on the other side. But we kind of need both. And so that's what I want to talk about today. Yeah.
Thank you. Thank you. So maybe I will give the chance to Jen to ask his question.
Yeah, actually, I don't rather have some questions, but rather than some thoughts, because you mentioned some the academics is like focusing on H index right now. But I feel like there is some so-called popular field and some like relatively like field with very small group of people. But I feel like it's also related to who actually promote this field. I mean, some field, for example, some like robotics field, for some materials field, I think it's like starting from one or two very famous professors, very famous scholars, they start to promote this field and it get very popular. But it is also some other like relatively so-called unpopular field, but it is also very interesting. For example, like Professor Higgins, your talk today, I mean, all the people attend your talk, the number of the people attending your talk is as many as the people attending those popular field talk. So I guess it's also like maybe we need some other ways to promote some so-called unpopular fields so that people, when they see them, they probably feel like, okay, it's actually very interesting and maybe it's worth putting some time and energy on this field. So that's what I'm thinking. Yeah. So
I mean, Jen, maybe the interesting thing to think about is you mentioned in a field like robotics or maybe in your field materials and so on. We all know there's these people who built a whole school, you know, who maybe 20 or 30 or 40 years ago wrote some very foundational papers that now whole disciplines are built around, you know, maybe there's a whole journal. I have a colleague at McGill, Michael Paidusis, who started the field of fluid structure interaction in the 1960s, which, you know, there's an entire journal and built around now. But it's interesting I would think an interesting exercise would be to go back and look at where they were at maybe 5 or 10 years after they published that seminal paper and compute what their H index would have been at that time. And I don't think it would have been very high, okay, because it takes time. It takes time to build those communities. I spent my sabbatical in 2010, 2011 with Vitaly Nestorenko at UC San Diego, who wrote a very innovative paper in the early 1980s about looking at discrete effects in shock waves and compression waves, just thinking about if you took a bunch of spheres and put them one after another and sent a pulse into that, what would that wave look like? And now there's an entire discipline built around looking at that. And he has this wonderful network of researchers all over the world working on this problem. But, you know, that paper, if you look at it, was published in 1983. It didn't get cited for about a decade. I mean, just 0 citations. And exactly. If he had been an assistant professor in a Western university now, he wouldn't have made tenure. You know, he would have been thrown out. And so that's what really worries me is the expectation that you should be racking up citations. And I'm as guilty as everybody. You know, every morning I check Google Scholar and see, did one of my new papers get cited? You know, there's 2 kinds of academics. Okay, there's those that admit they check their citations every day, and then there's those that won't admit to checking their citations every day. But we all do it. But you know, I just don't know if the effect that is having is good. I think citations are the correct metric. I think the citation is the correct way to look at the merit of a paper, because if you're doing something that's useful, it's going to collect citations. But it's just that the time scale, the expectation that if you're a postdoc or assistant professor, the expectations, you know, they really want to see your citations take off. And I don't know. I mean, it's just it's I think a real crisis that we're facing now.
Yeah, especially for young researchers.
Exactly.
Because when you apply for faculty positions, then they usually look at citations, how many papers you publish, what's the impact factor, and so on. So and also like I'm actually from solid mechanics, but in our field, when people want to publish papers, they usually pretend they are published in a materials field. So people always have some misunderstanding of you are doing materials, but we are actually just want to have the impressions on other people that we are doing materials papers, so that it's easier for us to publish on publish papers. But what we are actually doing is mechanics, but now it's rather very interdisciplinary, like research is very popular. Also for interstellar travel, as I was thinking, because I feel like, for example, you need to probably tune the structure and also the materials of the light cell. And then I can see some of your slides. Actually, it's kind of like a mechanics problem, sorry, the mechanics problems. And also, like, for example, like, because for now, the acceleration is too high, so it's too high for human beings, then probably we also need to engineer human beings ourselves. So to actually adapt to this kind of accelerations, which might be possible, like probably we can, I mean, if it's going to sci-fi, then we can upload our consciousness to some machine and which can take the load. And so I think in the future, in this particular field, it will also, like, probably in many years later, it will also be a very popular and interdisciplinary field. It is kind of, it can also kind of possible. Yeah, I feel like I kind of believe that. Yeah.
Yeah, I mean, the talking about whether we're humans or not, I think that was Carl Sagan's quote. He said the people that go to the stars won't be us, but there'll be people very much like us. You know, there'll be descendants from us, either heavily genetically modified or maybe some sort of human machine hybrid. You know, is probably who will go to the stars. Yeah.
Wonderful. It's a very interesting discussion, but concerning the time, I think you know, we have a lot of questions answered, and you know, Professor Higgins shared us a very interesting information. And yeah, perhaps I will conclude today's event at this point. And if you have any further questions, you can ask Professor Higgins directly by email, or you have interest in this field, you feel free to contact Professor Higgins, or you can go through us as well. And if you are interested in the future upcoming events of the Martlet Society, you know, remember to follow us on Twitter and WeChat, right? So is there any other announcement that Jen, you want to make?
I think the only one I want to announce probably is so the next talk will be given by Professor Jun Chen from UCLA, and so we are looking forward to seeing you, everyone there. Yeah.
Okay.
Yeah.
Okay. Thank you. Thank you very much for the invitation. I really enjoyed it, and I look forward to the future Martlets events.
Higgins. Yeah.
Thank you. Thank you for your time.
Thanks so much.
Yeah. And then have a good day and a good night.
Yeah.
Thank
everyone
you all.
Have a good day. Have a good weekend.
Yeah. Bye bye.
Bye bye.